into streams of particles that we see on the ground as the auroral substance. And what is responsible for that release of energy is the great debate of how aurora are stimulated. In particular, the substorms or the great increases in light intensities at a given instant. One of the things that is helpful for us is the following, is that the Earth's magnetic field acts like little wires, all right? So we have sort of a map in a way. So if you were to explore, you know where the aurora was actually created. You can image it like with D, these fantastic global images. You find a bright spot, all right? Now, if we could take that bright spot, right, and follow and look for the field lines that thread it, and we walked out into the magnetotail along that field line, right, that magnetic field line, which just behaves like that copper wire, somewhere out there, if I took a journey long enough, right, I'd come to the power supply. And that's what we're searching for. That's what has yet to be ever reported.
Using IC3 satellite data from out in the magnetotail, Edward Hohn's Los Alamos National Lab is tackling this question of the power supply. He is willing to present a detailed model of how he believes plasma in the magnetosphere behaves during a substorm.
To understand the Earth and the solar wind, one must understand the process of magnetic reconnection.
Plasma in the magnetosphere can be like two magnets. When two bodies of plasma, magnetized in opposite directions, are pressed together, like magnets, their magnetic fields will change direction and align to each other's opposite poles, north to south, so their magnetic field lines appear to reconnect to each other.
Because of enhanced reconnection at the front of the magnetosphere, magnetic reconnection increases, more energy is poured into the magnetotail in the form of magnetic field lines, and this squeezes down the plasma sheet. It causes it to sort of neck down. And the result of this is that oppositely directed field lines in the north and south part of the plasma sheet are pushed closer and closer together until, zap, all of a sudden, the oppositely directed field lines meet and reconnect across the current sheet. And very suddenly, and this happens, and it causes a very rapid injection of plasma toward the Earth, and this results in the brightening of the auroras in the night side of the auroral oval. But at the same time, this reconnection is also causing a cutting off of the plasma sheet. The plasma is jetting tailward, and the field lines tailward of the reconnection region are forming closed loops, closed circles. And eventually the last closed field line of the plasma sheet is severed, and it's no longer connected to Earth. There's nothing to keep it there, and it starts flowing tailward. And it's a large body of plasma on closed magnetic loops, and we call that a plasmoid. It carries something like a half of the energy that's previously stored in the tail. We had formulated these ideas from measurements made with satellites quite near the Earth, 100,000 kilometers from Earth, the IMP satellites and IC-1 and 2. Then an opportunity came along in 1983 to put the IC-3 satellite far down the tail, 1.5 million kilometers down the tail. And this was done, and one of the first things we discovered in the IC3 data was the passage of huge plasmoids occurring some half an hour after substorms.
There are other theories. So often in science, many could be partially right. It is complicated in the magnetosphere. Different scientists may be viewing portions of the whole to draw their conclusions. Besides seeking to understand the cause of the auroras, scientists want to predict storms. There are dangerous effects from the energy released during auroral disturbances. In the Earth-Sun system, the aurora gets its supply of energy from the magnetosphere. The magnetosphere depends on the solar wind, which receives its energy from the sun, especially following solar flares. This sequential transfer of energy can be used to make predictions of auroras. IC3 was an outrider sentry for the incoming solar wind, providing reliable data helpful in making short-term predictions, a half-hour lead before an auroral storm. Poker Flat used these predictions before launches. For longer predictions, magnetospheric and solar physicists traditionally study activity on the sun, sunspots, and solar flares to anticipate geomagnetic storms. At NOAA's Space Environmental Services Center in Boulder, their observatory is part of a worldwide network providing solar activity data to those concerned with auroral predictions. The Air Force sponsors space weather experiments because of their need to plan operations, warning or avoiding the impact of disturbances in the auroral environment. The center makes continuous observations using GOES, the geostationary weather satellite, which also points instrumentation at the sun. In addition, ground-based optical observatories worldwide watch the locations of activities on the sun for the kind of effect it would have on Earth. One of the problems is that not all of the solar flares cause intense geomagnetic storms or auroral displays. Some do, others don't. Shun Akasofu is one of the scientists who was challenged by this difficult problem and has improved predictions of auroras.
The location of solar flare is important. When the solar flare takes place near the center of the disk of the sun, then the gas comes straight and directly hits the magnetosphere. On the other hand, if a flare takes place near the rim of the disk of the sun, then the gas from that particular flare goes about 90 degrees away from us, so we don't get very much effect of it.
He charts the positions of the sun and Earth, determining when the solar flares line up with Earth. He also predicts the intensity of geomagnetic storms.
We're now looking down on the solar system from above. Those spiral pattern you see is a solar wind magnetic field. In order to predict the intensity of geomagnetic storm, we have to predict the power of the generator after solar flare. The power of the generator depends on the speed of the solar wind and intensity of the solar wind magnetic field and the direction of the magnetic field.
Akasofu's scheme on prediction will be fed into the Department of Defense main computer system to predict the times and locations of auroras for their data. The aurora is just the visible part of a large-scale electrical discharge phenomenon. Invisible, changing electric fields caused by the auroral discharge cause many other phenomena. An electric current of up to 1 million amperes flows along an aurora in the ionosphere. This current causes geomagnetic disturbances in high latitudes, and when currents vary, magnetic field changes induce electric currents in long conductors on Earth, such as long pipelines, power lines, and telegraph wires. The Trans-Alaska Pipeline, covering hundreds of miles in the auroral zone, physicists predict could have a greater risk of corrosion because of this increased ion migration. The pipeline company, Alyeska, however, checks the pipe carefully and uses coatings for protection from other sources of corrosion anyway. While they were checking the pipeline, they have found the instrumentation which measures the corrosion was unusable during magnetic storms. Power companies are regular subscribers to auroral warnings from NOAA. The longer the line, the larger the voltage the aurora induces. Associated current in the telegraph line during the intense aurora of 1897 was so strong that for 2 hours they sent messages between Boston and Portland, Maine, without a battery. Even modern lines can experience blackouts due to auroral storms. The currents surge intermittently through protective relay devices in the line and cause them to trip off, stopping that line's power transmission. The power lines have to be long enough to conduct currents. If there is such a problem during an auroral storm, the company can shut down the lines and reroute to others.
Oh, man.
There's ongoing interest in the possibility of biological effects from magnetic field changes. Some species of birds use the Earth's magnetic field to aid their navigation. Pigeon racers get sunspot forecasts because they fear they will lose birds during magnetic storms. When auroral events affect communications in circumpolar regions where transportation is also often unreliable, its impact is even more dramatic than for our technology-dependent cities. Emergency high-frequency radio is used to link the central, larger village's doctors with the outlying village's local health aides.
Okay, it sounds more like a hives, COVID and itching.
Hives, I think, because they're real big patches,
However, during an auroral disturbance, changes in the ionosphere disrupt this frequency's radio signals.
Yeah, that's good.
The challenge to meet this vital communication need for Alaska bush villages' health led to an advanced satellite telecommunications system that is a model to the developing world. Scientists and engineers helped the state to improve communications with a higher frequency satellite system. The health aides could relay symptoms to doctors and receive replies on treatments and decisions on whether to call in air rescue or take the patient to the doctor for examination. Ever since this development in the 1970s, Alaskan villages have been connected to each other and to the rest of the world by satellite for television, radio, and telephone.
It's got a lot of interesting stuff.
Laverne and Shirley at 7:30.
Happy Days in Laverne and Shirley.
Soon I see the little, you know, the, like, breathe. I shut me, just pass to that wall, pass to, like you know.
Within this auroral zone surrounding the Arctic, geography, terrain, and climate already strain many technical systems for communications, radar, and transportation. It is in these same geographic extremes, where there are highly charged ionized particles from the aurora, that national defense systems have to operate.
Elmendorf Airways, Foggy 66 on 5656 upper.
Froggy 66, Froggy 66, this is Elmendorf, sir. Be advised I have you weak readable. Hard copy, Elmendorf.
Elmendorf Airways, come in. Elmendorf Airways, Foggy 66, unable this transmission.
Some long-distance over-the-horizon radar uses frequencies, UHF, that irregularities in the ionosphere make unreliable. Radar for the detection of transpolar aircraft flights sometimes observes signals which could disguise approaching aircraft. In an auroral environment, high-tech surveillance systems are threatened. Radar detection, thermal detection of exhaust plumes of aircraft and missiles in an auroral background become very complicated. Designers need to account for the aurora. Through knowledge of the aurora's wavelengths and the ability to predict them, these problems are manageable. Low-altitude communication satellites of interest to telecommunications as well as to the military suffer increased drag in the heated upper atmosphere of the aurora and can be degraded to the wrong orbit or burn up in the atmosphere. An orbital change would make them ineffective for the military. The problem has more impact because satellites are supposed to compensate for loss of communications on HF. NASA, earlier in the space program, underestimated such auroral effects on their satellites. After several missions, the plan was to boost the Skylab vehicle into a permanent work location to maintain it for 10 years. The sunspot cycle was 3 times more intense than they expected. A space shuttle mission planned to rescue it was not ready in time to push it out into orbit. The vehicle experienced a higher drag than expected from the heating in the atmosphere, re-entered the atmosphere, and plunged into the ocean near Australia. Astronauts, too, are exposed to dangerous high-energy particles from the sun and auroral electrons from the magnetosphere. The space shuttle offers plenty of shielding for working inside. However, during EVAs, extravehicular activities, there is a radiation hazard. X-rays generated by the auroral electrons eventually will penetrate the spacesuits and could cause sterility or death. The spacesuits are enough protection for current missions, activities, and orbits. In the future, though, with longer EVAs, transpolar orbits, and missions at distances where there's greater particle precipitation, the risk from radiation increases. As scientists experiment more in the radiation belts, they will try to improve conditions so that it will be less dangerous for work outside space vehicles. Increasing the world's knowledge of the aurora and related effects is preparation for the future, to extend exploration in many areas of science, in space and on Earth. Robert Hellawell's team is preparing for the future using high-powered radio transmitters to study the radiation belts and the mechanisms which cause auroral disturbances. They are also recording the man-made and natural sound coming from these invisible particles in space. Their experiments could go into space on the shuttle.
What we are hearing are natural electromagnetic signals coming out of the magnetosphere, which have been created by lightning discharges or by radio transmitters or by natural radiation from the plasma itself. And what is most remarkable is that the Earth's plasma can create intense radio waves of very coherent nature that sound like birds waking up in the morning, which gives rise to the term dawn chorus, and which is really the reason I think that we're all working on this particular subject. There is a source of electromagnetic energy, and that energy storage mechanism is the Van Allen radiation belts. The particles that create the radiation are acting collectively, just as they do in a laboratory oscillator, to create a very large signal. What's exciting is that this process is present throughout the cosmos, as far as we can tell, and I suppose it's everywhere that you have a plasma. The transmitter on the shuttle is, in an oversimplified way, intended to extend the experiments that are currently being performed from the ground.
Manned space shuttle flights in transpolar orbits open up numerous opportunities for aurora-related and magnetosphere research. The shuttle could fly through both the northern and southern auroras with each pass. Using the spacecraft to conduct such experiments as barium releases would add an interesting dimension. Tracers released farther away from the Earth by satellites could provide data to solve the mystery of the magnetosphere's power supply. In studying the aurora, scientists have an accessible laboratory to space. The auroral zone is more like the rest of the universe than is anything on Earth. What we tend to think of as our universe, Earth's rich atmosphere, the states of matter here, solids, liquids, and gases, the sunlight we can see that is the right warmth for the systems which depend on it, is really the exception in this universe. Space isn't a void, empty. It's filled with plasma, various gases that are in the fourth state of matter. They are so hot that they remain an unstable mixture of positively and negatively charged particles. 99% of the matter in the universe is in this state. We find such a plasma in the auroral zone. The more we learn about the aurora's plasma, the more we learn about the universe. Plasma is the Earth's ultimate energy source, the heat of the stars, thermonuclear fusion, the power we would never run out of. Los Alamos National Lab and others are conducting magnetically confined fusion research, thermonuclear power experiments. To generate power, scientists have to reproduce and contain heat equal to the sun's. For this experiment, they heat and compress plasma in a vacuum tube to 10 million degrees, accelerate it, and then trap it into a containment vessel for study. These experiments have many similarities to the Earth's magnetosphere power generator, but in a smaller form with more compressed plasma.
As in the magnetosphere, magnetic reconnection of the field lines occurs in this device and is extremely important in providing the good containment of our heated plasmoids. Another similarity between these laboratory and space plasmoids is their ability to be launched and propagated over relatively long distances.
Perhaps the most important region is in the understanding of plasmas, the basic laws of plasma. How does matter in the plasma form behave? The Very Large Array radio telescope in New Mexico was a real breakthrough. It provided very detailed observations, high-resolution observations of radio galaxies. And one of the remarkable features of these radio galaxies are what they call galactic jets, jets of plasma coming, streaming many thousands of light years in both directions from the centers of these galaxies. They're very suggestive of closed loop structures, plasmoids, just like we see in the magnetotail of the Earth.
The aurora provides exceptional conditions in which deep space comes to meet Earth. Those who study the aurora can study plasma in its natural state, directly measure it, and then infer about distant conditions. What we learn about plasma is applied to understanding other galaxies, stars, nebulae, and quasars. Even study of our solar system requires this knowledge. The other planets have magnetic fields, and some have auroras. In order for the aurora to appear on a planet, a magnetic field, the solar wind, and an atmosphere are needed. Venus has the atmosphere, but not enough magnetic field. Mercury has enough magnetic field, though not enough atmosphere. Saturn and Jupiter and Earth have enough of both. If an extraterrestrial were to come to our solar system, he would notice these 3 planets over the others because of the strength of their radio waves generated by auroral processes, the energy released by the magnetic field and the solar wind. The Pioneer and Voyager missions observed Jupiter's magnetosphere. It's 10 times that of Earth. It's so large, Voyager could record its auroral effects in the daylight. Io, its moon, is part of it as the conductor for Jupiter's lights. If we could see it, Jupiter's magnetosphere would look as big as the sun. Auroras are an indicator of many physical conditions about the planets. The engineering of a space station, the U.S.'s Space Race Challenge, also requires knowledge of the plasma environment. A station is out in the intense electron heat and hot plasmas of the magnetosphere. Since people will be spending more time there, depending more on complex technical systems for support, they will need to understand it better. In studying the aurora, scientists are developing knowledge about our next environment, the rest of the universe.
Competition is forcing us forward to try and solve the problem of what the underlying physics is. If we understand that physics, you can go forward into even astrophysics. You can go to the large galactic systems, the very energetic systems, which are just plasmas on a huge scale. almost incomprehensible in dimensions to what we work with and live with on Earth, and try and understand them.
The first satellites carried instruments to learn about the auroras. So the study of the auroras has led to a great intellectual adventure for mankind, and is continuing.
Production of this program was made possible in part by grants from the Alaska Council on Science and Technology, the Corporation for Public Broadcasting through the Pacific Mountain Network Program Fund, and the University of Alaska Foundation.